All right, so here we look at another way of determining convergence and divergence by using integrals. So this thing is called the integral test. So in the integral test, it says if we have a function f that is positive, continuous, and decreasing for x greater than or equal to 1. Now that x greater than or equal to 1, we can change that a little bit. I'll explain that in a second. And a sub n equals f of n, then this summation and this integral will both do the same thing. They're either both going to converge or both going to diverge. So let's take a closer look at this. Look at this integral right here. Okay? This is the f that needs to be positive, continuous, and decreasing for x greater than or equal to 1. The reason why they're using x greater than or equal to 1 is because this integral starts at 1. If that integral were to start at 5 to infinity, then we would change this number to a 5. If it was 10 to infinity, we change this number to a 10. So this number right here, x greater than or equal to 1, that's not set in stone. Then we're going to look at this series here. Okay? Now, the starting point of the integral and the starting point of the series have to be the same, and they're both going to infinity. Okay? So we're going to match those up. Then what it says is that a sub n and f of n have to equal each other. So basically the function here has to generate the same thing that the series generates. But if we can do this, we know how to do this type of integral. This is an improper integral. We know how to do it. We know how to get the answer. And we know whether or not this integral is going to converge or diverge. And if we can figure out what happens to this integral here, then that'll tell us what happens with the series, because both of them will work the same way. Let's do an example. I think it'll clear things up. So let's erase all this business here. All right. So if we look at f of x equals x over x squared plus 1. So we're looking at this series. We're trying to figure out what happens with this series. Does it converge or diverge? Since it's not geometric, the nth term test wouldn't apply because this thing is going to go to 0. And I don't want to do the partial fraction the partial sum concept for determining if this thing converges or diverges. We're going to do this integral test. So I'm going to look at this function x over x squared plus 1. Why? Because this function and this series would give me the same thing in terms of if I plug 1 into here or plug 1 into here, I get the same answer. If I plug 2 into here, if I plug 2 into here, I get the same answer. So that's why I'm going to look at this function. First off, is this function positive, continuous, and also decreasing? Now this will be for x is greater than or equal to 1 because that's where the series is starting. Is this true? Well, I think you can clearly see that this would definitely be positive, so that's good. Continuous, well, as long as the denominator is not 0, which it never is because x squared plus 1 never equals 0, and especially for these x's it never is, it's continuous. And decreasing, as x gets bigger and bigger and bigger, the denominator is going to grow faster than the numerator will. So this will definitely go to 0, which means it's going to be decreasing. Okay? So all those things are going to hold. I'm not going to make you prove any of those things, but you can clearly look at the function and see if they're all happening. So then what I'm going to do is I'm going to say, okay, let's do the integral from 1 to infinity of x over x squared plus 1. And if we can do this and figure out converge or diverge, then that'll tell us what's going on with this series. Well, we could do this. This is an improper integral. We have the limit as b goes to infinity of the integral from 1 to b of x over x squared plus 1 dx. Then if we use substitution, let's say u equals x squared plus 1, du equals 2x dx, divide by 2, you're going to end up with the limit as b goes to infinity. This is going to turn into a 1/2 integral du over u. So it's going to be a logarithm integral. So we're going to get 1/2 log of x squared plus 1 between 1 and b. We'll plug in b, then we'll plug in 1. We're going to get the limit as b goes to infinity of 1/2 log of b squared plus 1 minus 1/2 log of 2. As b goes to infinity, clearly this thing's going to go to infinity, and the log will also go to infinity. So we're going to get infinity minus this 1/2 log 2. Well, infinity minus some random constant, that's still going to be infinite. So what does that tell us? The integral diverges. Well, if the integral diverges and the integral test says both will do the same thing, then we could say by the integral test, the series n over n squared plus 1 also diverges. Okay. So just another thing in our bag of tricks that we can use to determine whether or not a series converges or diverges. Now there's a problem to the test. The problem with the test is it doesn't say what the series will converge to, it just says it's going to converge. So let's look at the next example. All right, let's take a look at this question here. So we have the series, and I really should put some instructions here. Does the series converge or diverge? So if we're trying to determine that, so we have a list of things, right? We have the partial sums way of doing it, which is the first thing we talked about when it came to series. I will be honest with you and tell you that we're not going to use this a ton. This is the way we got started, but it's really difficult to show a lot of series are going to converge or diverge using this. I mean, it's really nice in that it tells you if it converges and then what it converges to, but it's fairly difficult to use for a lot of series. We have geometric. We have geometric, which this is not. We have nth term, which is not going to work because this does go to 0. Nth term only works if it doesn't go to 0. And now we have the integral test. Well, how are we going to determine if integral test is a good one to use? Well, if this were a function, would you be able to integrate it? That's the big question. If you saw this as a function, 1 over x squared plus 1, would you be able to integrate it? And if the answer to that is yes, then this is a good test to use. So in this case, the answer is yes. So we're going to use the integral test for this one. Right, so we're going to look at f of x to be 1 over x squared plus 1. Is that positive, continuous, and decreasing? For x, in this case again, greater than or equal to 1. And yeah, positive, yeah, continuous, yeah, decreasing, for all the same reasons, right? Positive, clearly. Continuous, yeah, this is never 0 for these x's. And decreasing, since this thing is going to 0, as x gets bigger, this will get smaller, so decreasing. So we're going to do the integral from 1 to infinity of 1 over x squared plus 1 dx. Now, we'll have to do the limit as b goes to infinity of 1 to b of 1 over x squared plus 1 dx, because it's improper. The integral is real easy to do. We're going to use arctan. So we're going to get arctan x from 1 to b, where the limit as b goes to infinity of arctan b minus arctan 1. If you remember, as b goes to infinity, arctan b goes to pi halves, and arctan of 1 is pi fourths. So pi halves minus pi fourths is pi fourths. So we could say the integral converges to pi fourths. Now, what about the series? By the integral test, the series also converges. But notice I didn't say converges to pi fourths, because we can't go that far. We can just say that it converges. Just because the series, the integral converges to pi fourths doesn't mean the series will converge to pi fourths. All the integral test says is if this converges, the series will converge. But it doesn't say that they'll converge to the same thing, and they don't really. But the fact that they converge is just saying that they behave the same way. They don't necessarily have the same value to them. So be careful with that. So the one problem with the integral test is we don't know what the series will converge to, but at least we're able to figure out if it converges. All right, so we're going to determine if this one converges or diverges. We're going to use the integral test again. The reason why we're going to use the integral test again is if we look at this thing, if this were a function, it would be a function that should be fairly easy to integrate. We can't use geometric series because it's not geometric series. We can't use nth term test because this thing goes to 0. The partial sums is going to be way too cumbersome. So if we look at, say, the function f of x equals 1 over x ln x, and we think about, is that positive, is it continuous, and is it decreasing for x greater than or equal to 2? Now greater than or equal to 2 because the series starts at 2. And I think clearly you could see that that would all check if we use these x's. Definitely positive because we're plugging in positives here. Definitely continuous because this will never be 0 because we're bigger than 2. If we were at 1, that would be 0 and we would have a problem. But since we're going x greater than or equal to 2, we're good. It's definitely decreasing as x gets bigger, the whole fraction will get smaller. So let's look at the integral from 2 to infinity of 1 over x ln x dx. Clearly improper, so we'll do the limit as b goes to infinity of the integral from 2 to b of 1 over x ln x dx. If u equaled ln x, du would be 1 over x dx. So substitution will work here. 1 over x dx, that's our du. There's our u. So if we look at this integral, it's going to be the limit as b goes to infinity of the integral from 2 to b of du over u. So it's going to be a logarithm integral. So we have the limit as b goes to infinity of the log of u. U was the log of x, so we get the log of x between 2 and b. So now we're going to plug in b and plug in 2, so we have the limit as b goes to infinity of the log of b minus the log of 2. And this is just a constant. It doesn't have any b's in it, so log of 2. You can't do anything better, just leave it. This one, though, as b goes to infinity, the log of b will go to infinity, and the log of something that goes to infinity also goes to infinity. So anyway, this whole thing is going to go to infinity. So we get infinity minus the log of 2. What does that tell me? What it tells me is that this is basically infinite. So the integral diverges. Therefore, by the integral test, the series also diverges. Okay? So when do you use the integral test? When the series looks like a type of function that should be fairly easy to integrate. One major series that comes out as a consequence of the integral test, or is easily proven, I should say, by the integral test, is something called a p-series. Now later in the semester we're going to talk about something called a power series. This is not that. This is a p-series. So p-series. Okay? And so any series that looks like this, the sum of n equals 1 to infinity of 1 over n to the p, where p is a positive constant, would be considered a p-series. These are pretty easy series to work with the integral test, but we can just generally do it and see what the different powers will actually do to the series. If we have a specific power of 1, so 1 over n to the first, which would be this series right here, so 1 plus a half plus a third plus a fourth, which is that mystery series we've looked at a couple of times now and haven't been able to apply any of the tests that we've looked at so far to. We'll be able to look at it now, but this type of series is called a harmonic series. It's a p-series, but more specifically we categorize it as a harmonic series. And something that has this form, this should be a times n, not a sub n. So a times n plus b. Okay. This is called a general harmonic. So you can't really see that. So it's the sum of 1 over a times n plus b. That's called a general harmonic series. So what we look at is for a p-series. If we look at any general p-series, a p-series will converge if the power is greater than, simply greater than 1. Okay. Ignore this or equal to. It's only when it's greater than 1. And will diverge when p is less than or equal to 1. Okay. So some little issues here with the notes, but I fixed it. So p greater than 1, converge. P less than or equal to 1, diverge. So if I said, here's a series, n equals 1 to infinity of 1 over n squared, what happens to it? We'd say, oh, this is a p-series. P is 2. Since that power is greater than 1, that p is greater than 1, the series converges. Or if I said, how about this one? The sum of n equals 1 to infinity of 1 over n to the 2/3. You would say, oh, well, that's a p-series. P is 2/3. That power is less than 1. Therefore, the series diverges. And if I said, how about this one? N equals 1 to infinity of 1 over n to the first, which is the one we've tried to look at a couple of times. You would say, oh, that's a p-series. More specifically, harmonic series. And since that power is 1, it diverges. Now why? Why is this the case? Why are these powers going to make it converge and these powers going to make it diverge? Well, the integral test will tell us that. So let me make a little space in here and we can see this. So 1 over n to the p is a pretty easy function if it were a function to integrate, because we could just use power rule for most cases. We may need to use a logarithm for a power of 1. But let's look at the function, or let's say the integral of 1 to infinity of 1 over n to the p dn. Well, you guys, I'm sure, don't like the n's, so let's say x to the p dx. Okay. Now, we got to split this into two options. P equals 1, P doesn't equal 1. Because if P equals 1, we're going to get the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. In which case we have to use a logarithm. So it will be the limit as b goes to infinity of the log of x between 1 and b. Whereas if p doesn't equal 1, we would go, okay, we got the limit as b goes to infinity of the integral from 1 to b. We'll have to bring this x up, x to the negative p dx, and we'll use the power rule. Now we can use the power rule as long as the power wasn't 1, and we already took care of that in the first instance. So we have the limit as b goes to infinity of, this will be x to the negative p plus 1 over negative p plus 1. When you integrate, you add 1 to the power. Now to go between 1 and b. Let's take a look at this one a little bit closer. I'll bring it up here so I have some space. I'll plug in b, I'll plug in 1, and I end up with the limit as b goes to infinity of log of b minus log of 1. Well, log of 1 is 0, so we're really just doing the log of b as b goes to infinity. We should know by now, especially after the last example, that goes to infinity. If that goes to infinity, the integral back here with p equal to 1 diverges. If the integral diverges, then the series diverges. So that's why we need the or equal to 1 here in the divergence section of the p-series test. So let's look at this now. Here. So we plug in b, we'll plug in 1. Remember, we're plugging in for x. Instead of writing minus p plus 1, I'm going to write 1 minus p. So what I'm going to have is, I have the limit as b goes to infinity of x to the 1 minus p over 1 minus p between 1 and b, which will give me the limit as b goes to infinity of b to the 1 minus p over 1 minus p minus 1 to the 1 minus p over 1 minus p. Well, think about this. 1 to the 1 minus p. P is a constant. So no matter what p is as a constant, this is always going to be 1. So I can say, okay, this thing right here, this is 1 no matter what. So this is 1 over 1 minus p. That doesn't have any b's in it, so this limit's not going to affect that whatsoever. Okay? And that's just going to be some constant dependent on p. Now the problem is here. If I'm doing the limit of this as b goes to infinity, there's two things that can happen depending on what p is. So if I split this into two groups, one where p is greater than 1 and one where p is less than 1. When p is greater than 1, this is a negative exponent. And if that's a negative exponent, this whole b deal goes to the denominator. And as b goes to infinity, this whole thing here is going to go to 0. Okay? If that's going to go to 0, you're simply left with 0 minus 1 over 1 minus p, which will be some constant. If you get a constant, that tells me that the integral diverges. If the integral converges. If the integral converges, then the series converges. For p less than 1, this is a positive exponent. B to a positive exponent, this stays up in the numerator. As b goes to infinity, this thing all goes to infinity. Well, infinity minus some constant, that whole thing is infinite, and therefore the integral diverges. And if the integral diverges, the series diverges. So, again, look, p greater than 1 converges. P less than or equal to 1, less than 1 or equal to 1, diverges. So that's the reason why the p-series test is what it is. I mean, long story short, you just need to know this information in here, the correct information, not what I have here, so not this, and you need to add this. But p greater than 1, converge. P less than or equal to 1, diverge. And that's what's going to happen to a p-series.